Welcome. Welcome to our tutorial on security techniques for microservices. In today's rapidly evolving digital landscape, microservices have become a cornerstone of modern application architecture. They offer flexibility, scalability, and faster development cycles. However, with these benefits comes a critical responsibility that's often overlooked. When teams embark on designing and building a new microservice, there's a natural tendency to focus primarily on functionality and feature development. It's exciting to create something new, to see it take shape and deliver value. But in this rush to build, we often underestimate the complexity and effort required to address crucial non-functional requirements. I want to emphasize this point. Availability, resiliency, performance, and especially security are not afterthoughts. They are fundamental aspects of your microservice that demand attention from day one. Too often, teams commit to delivery timelines without fully considering these non-functional requirements. This oversight can lead to vulnerabilities, performance issues, and ultimately, a service that's not fit for purpose in a production environment. In fact, during my time at Amazon, our team was tasked with developing a new service to host the landing pages for all high-velocity events, including Prime Day, Black Friday, and Cyber Monday. While we successfully implemented the core functionality within 3 months, it took an additional 6 months to elevate our service from a proof of concept to a robust Tier 1 solution. This maturation process was crucial to meet all non-functional requirements necessary to handle the immense traffic and deliver the gold standard experience expected for events like Prime Day. So before we dive into specific security techniques, I urge you to shift your mindset. When planning your microservice, give, at the very least, equal weight to both functional and non-functional requirements. Set realistic goals that account for the time and effort needed to build a secure, resilient, and high-performing service. In the next few minutes, we'll embark on a comprehensive exploration of key security techniques and mechanisms crucial for microservice owners. We'll start by diving into authentication and authorization, covering JSON Web Tokens, JWT, for secure, stateless authentication, and discussing how OAuth 2.0 and OpenID Connect can fortify your microservices. We'll then move on to API security, examining the role of API gateways and the critical importance of input validation. We will continue with network security, where we'll explore service meshes and the principle of network segmentation. We'll also touch on the vital practices of monitoring and logging, emphasizing their role in maintaining a secure ecosystem. Finally, we'll round off with secure development practices, including dependency management and coding guidelines. And, by the end of this tutorial, my goal is that you'll have a clear, actionable understanding of these essential security measures, empowering you to implement robust security protocols in your microservices architecture from the ground up. Last but not least, remember that in the world of microservices, security isn't just a feature, it's a fundamental requirement. Let me say it very clearly. Security should not be an afterthought. When building a microservice, security demands attention from day one. Okay, now that I scared everyone away, let's dive right in. Let's first dive into authentication and authorization, two critical components of microservice security. Authentication is the process of verifying who a user or service claims to be. Authentication is like showing your ID at the entrance of a building. It's the process of proving you are who you say you are. When you log into a website or app, you're going through authentication. You might do this by entering a username and password, or using your fingerprint or face scan, or entering a code sent to your phone. The system checks if the information you provided matches what it has on record. If it does, you're authenticated and allowed in. In simple terms, authentication answers the question, are you who you claim to be? Authorization, on the other hand, determines what that authenticated user or service is allowed to do. Which rooms they can enter, so to speak. It's like having different access cards in that building. Some people might only be able to enter certain rooms, while others have access to everything. In a microservice, a regular user might only be able to view their own profile. An editor might be able to change content on a website, and an admin might have full control over all settings. So, cutting to the chase, authorization answers what are you allowed to do here. Both work together to keep systems secure. First, you prove who you are. You get authenticated. Then the system decides what you're allowed to access or do. The system authorizes you. Now that we understand the concepts and differences between authentication and authorization, let's talk about JSON Web Tokens, or JWTs. A JWT is token format. It is not a protocol or a framework. It's essentially a compact, self-contained way of securely transmitting information between parties as a JSON object. Here's how it works. When a user logs in, the authentication server creates a JWT containing a payload of user data and a signature. This token is then sent back to the user. For subsequent requests, the user includes this token, allowing each microservice to verify the user's identity without needing to contact the authentication server again. The beauty of JWTs lies in their statelessness. What does it mean? Since all necessary information is contained within the token itself, your services don't need to query a database or session store to validate the user on every request. This makes JWTs particularly well suited for microservices architectures, where scalability and performance are key. Moving on to OAuth 2.0 and OpenID Connect. OAuth 2.0 is an authorization framework, not an authentication protocol. OAuth enables applications to obtain limited access to user accounts on an HTTP service. To be more precise, it's designed for delegating access to resources, allowing third-party applications to access user data without sharing the user credentials. It's like a valet key for your car. It provides just enough access to park your car, but not enough to access the trunk or drive across the country. To simplify, OAuth 2.0 answers the critical question: what the user can access. And to take a step back, JWT can be used within OAuth 2.0 as a token format. Now, let's talk about OpenID Connect. OpenID Connect builds on top of OAuth 2.0, adding an identity layer and providing user authentication capabilities. It allows clients to verify the identity of the end user and to obtain basic profile information. To simplify, OpenID answers who the user is. Now, to fully close the loop on what we discussed earlier, let me add that OpenID uses JWT as the format for ID tokens. To wrap up on this, OAuth 2.0 and OpenID Connect form a powerful duo for securing your architecture. OpenID handles authentication by verifying user identities, while OAuth 2.0 manages authorization, determining what resources users can access across different microservices. OpenID is widely used for enabling single sign-on, or SSO, integrating seamlessly with popular identity providers like Okta, Ping Identity, OneLogin, Google, Microsoft Entra ID, and so on. In practice, these technologies typically work in tandem with applications using OAuth 2.0 and OpenID together for comprehensive authentication and authorization. And they utilize JSON Web Tokens as the format for both access and ID tokens. Okay, let's now dive into API security. At the heart of this security model is the API gateway, which acts as a centralized entry point for managing and securing access to your microservices. API gateways play a crucial role in enforcing security policies. They handle authentication, ensuring that only verified users or services can access your APIs. This can be implemented through various methods such as OAuth, API keys, or JWT tokens. Another key function of API gateways is rate limiting. This prevents abuse and ensures fair usage of your services by limiting the number of requests a client can make within a given timeframe. For instance, you might set a limit of 1,000 requests per minute for each client. If exceeded, the gateway will throttle or reject additional requests, protecting your services from being overwhelmed. API gateways also facilitate monitoring, allowing you to track API usage, detect anomalies, and audit access patterns. This visibility is crucial for identifying potential security threats and ensuring compliance with security standards. Now, let's emphasize the critical importance of input validation and sanitization. Every input to your API must be treated as potentially malicious. By validating and sanitizing all inputs, you can prevent common vulnerabilities such as SQL injection and cross-site scripting attacks. This means checking that inputs are of the expected type, format, and length, and removing or escaping any potentially harmful characters. Remember, the security of your microservices is only as strong as your weakest link. By leveraging API gateways and implementing rigorous input validation, you create a robust first line of defense for your microservices architecture. Let's move on and discuss network security. Today, we'll focus on two key concepts: service mesh and network segmentation. First, let's talk about service mesh. A service mesh is a dedicated infrastructure layer that handles service-to-service communication in a microservices architecture. To simplify even further this explanation, consider a service mesh as a helper function to all microservices that has few important roles. 1. Make sure messages get sent correctly between services. 2. Keep everything secure, like a protective shield. 3. Help check if a service is working okay and possibly help automatically fix things if something goes wrong. So a service mesh is basically a smart traffic controller for microservices, making sure everything runs smoothly and safely in a big, complex digital playground. One of the most important features of a service mesh is its ability to implement mutual TLS or MTLS. With MTLS, both the client and server authenticate each other, ensuring that all communication is encrypted and verified. This two-way authentication significantly enhances security by preventing unauthorized access and eavesdropping. In practice, MTLS works by having each service present its own certificate. The service mesh verifies these certificates, establishing a secure, encrypted channel for data transmission only after both parties have successfully authenticated each other. This process happens automatically within the service mesh, reducing the burden on developers to implement complex security protocols. Now, network segmentation. This technique involves dividing your network into smaller, isolated segments or subnets. This architectural approach creates discrete zones that separate different users, devices, applications, or traffic flows within an organization's network infrastructure. In a microservices context, this means grouping related services together and limiting communication between different segments. Network segmentation is crucial because it limits the potential damage of a security breach. If an attacker gains access to one segment, they can't easily move laterally to other parts of your network. This containment strategy is particularly important in microservices architectures, where you might have dozens or hundreds of services. Implementing network segmentation can involve techniques like using virtual networks, firewalls, and access control lists. By carefully controlling which services can communicate with each other, you create a more secure and manageable environment. Remember, both service mesh and network segmentation work together to create layers of security. The service mesh ensures secure communication within and between segments, while segmentation provides isolation and containment. By implementing these techniques, you can significantly enhance the security posture of your microservices architecture. Let's turn our attention to two critical aspects of maintaining a secure microservices environment: centralized logging and real-time monitoring. First, centralized logging. In a microservices architecture, you're dealing with numerous independent services, each generating its own logs. Without a centralized logging system, you'd be drowning in a sea of disconnected data, making it nearly impossible to spot security issues or troubleshoot problems effectively. Centralized logging solves this by aggregating logs from all your microservices into a single, searchable repository. This gives you a holistic view of your entire system. When it comes to security, this is invaluable. It allows you to correlate events across different services, making it easier to detect patterns that might indicate a security breach or an ongoing attack. For instance, if an attacker is probing multiple services for vulnerabilities, you'd see these attempts across various logs. With centralized logging, you can quickly connect these dots and respond before any real damage is done. Tools like CloudWatch, CloudTrail, Azure Monitor, or Cloud Logging are invaluable in this realm. Moreover, centralized logging is crucial for forensic analysis. If a security incident does occur, having a complete, chronological record of system events can help you understand what happened, how it happened, and how to prevent it in the future. Now, real-time monitoring. While logging gives you a historical view, real-time monitoring provides immediate insights into your system's current state. It's like having a security camera that alerts you the moment something suspicious occurs. Real-time monitoring tools continuously analyze metrics and logs, looking for anomalies or predefined security events. When something unusual is detected, these tools can trigger immediate alerts, allowing your team to respond quickly to potential security threats. For example, a sudden spike in failed login attempts across multiple services could indicate a brute force attack. Real-time monitoring would detect this pattern and alert your security team, immediately allowing them to take swift action to block the attacker. Furthermore, real-time monitoring can help you detect and respond to more subtle security issues. Unusual patterns in API usage, unexpected changes in network traffic, or anomalies in resource utilization could all be early indicators of a security problem. By combining centralized logging with real-time monitoring, you create a powerful security information and event management system. This gives you both the historical context and the immediate awareness needed to maintain a strong security posture in your microservices environment. Remember, in our world, knowledge is power. The more visibility you have into your system, the better equipped you are to protect it. Okay, we're almost at the end of this tutorial. But before we conclude, let's talk about secure development practices, focusing on two critical areas: dependency management and secure coding practices. Let's be honest here. We rarely build everything from scratch. We rely on external libraries and frameworks to accelerate development. However, these dependencies can be a double-edged sword when it comes to security. Every dependency you introduce into your project is a potential vulnerability. Attackers often target popular libraries, knowing that a single exploit can affect thousands of applications. This is why regularly updating your dependencies is crucial. So, please set up automated processes to check for updates and security advisories. Tools like Dependabot or Sneak can automatically create pull requests when updates are available. But don't just blindly update. Test thoroughly to ensure the updates don't break your application. Equally important is vulnerability scanning. Use tools that can scan your dependency tree for known vulnerabilities. Many of these tools integrate with your CI/CD pipeline, allowing you to catch potential security issues before they make it to production. Last, keep in mind that dependency management is not a one-time task. It's an ongoing process that requires constant vigilance. Moving on to secure coding practices. While tools and automation are great, they can't replace good old-fashioned secure coding. Start by establishing secure coding guidelines for your team. These should cover things like input validation, output encoding, proper error handling, and secure data storage. OWASP provides excellent resources for secure coding practices specific to microservices. Code reviews are another crucial aspect of secure development. They're not just about catching bugs or improving code quality, they're an opportunity to spot potential security issues. So, train your team to look for security vulnerabilities during code reviews. This could include things like hard-coded credentials, inadequate access controls, or improper handling of sensitive data. Consider as well implementing a security champion program where team members receive additional security training and act as the first line of defense against potential vulnerabilities. Automated static code analysis tools can complement human code reviews. These tools can catch many common security issues and enforce your coding standards automatically. Finally, and you should already know it, secure coding is everyone's responsibility. It should be baked into your development process from the start, not tacked on at the end. By focusing on both dependency management and secure coding practices, you create a solid foundation for building secure microservices. It does require ongoing effort and vigilance, but the payoff in terms of security and peace of mind is well worth it. As we conclude this journey through microservices security, let's recap the key points and highlight some overarching best practices. We've covered authentication and authorization, emphasizing the power of JWTs and OAuth 2.0. We explored API security, focusing on the crucial role of API gateways and input validation. We delved into network security, discussing the benefits of service meshes and network segmentation. We also highlighted the importance of centralized logging and real-time monitoring for rapid threat detection and response. Lastly, we stressed the significance of secure development practices, including rigorous dependency management and adherence to secure coding guidelines. To tie it all together, remember these three overarching best practices. First, implement the principle of least privilege. Every service, user, and process should have only the minimum permissions necessary to perform its function. This limits the potential damage from any single point of compromise. Second, integrate automated security testing into your CI/CD pipelines. This ensures that security checks are performed consistently and frequently, catching vulnerabilities before they reach production. Finally, Regularly conduct security audits and penetration testing. These practices help identify vulnerabilities that automated tools might miss and ensure your security measures are truly effective. Security in a microservices architecture is an ongoing process, not a one-time task. Stay vigilant, stay informed, and always prioritize security in your development and operations processes. And, as always, for more insights on building robust, secure, and scalable systems, don't forget to subscribe to our channel. See you next time.